Hi folks, so this question here, what we're going to do is, it's 4 questions here. They're from the 2026 mock paper from the ExamCraft company. As always with these kind of questions here, there's going to be 4 questions on the exam and you're going to have to do 3 of them. For the purpose of this video, I'm going to do them all, so I'm going to start here with A1, on to A2, A3 and finish with A4. So starting with this one, so I'm going to zoom in there, let's set that one up. So this question here is based on the topic of conics. Okay, so it's A1, the exam paper. It says here the image below shows a modern building with an archway in the shape of a parabola, and you can see the parabolic curve there where the archway is. Okay, the drawing on the right shows the axis AA1, which is this line here of the parabola. We've got the directrix DD1. Okay, the directrix and the axis will always be perpendicular to each other, and a focus F of a similar parabola. P is a point on the directrix. Okay, so they tell us that P is a point on the directrix. Part A, locate the vertex and draw a portion of the parabola. Now, if you are used to doing conics in school, when you're doing conics in school, you learn about eccentricity. The eccentricity of the parabola is 1:1. So where the axis and the directrix meet, because the eccentricity is 1:1, we can do a line out at 45 degrees. So I'm going to put that line actually in green here. That line there is my line of eccentricity. Okay, so line of E. So eccentricity line. Okay, line of eccentricity. Okay, now how do I find the vertex? Well, from the focus, you always go back at an angle of 45 degrees, and where it hits the line of eccentricity, go perpendicular to the axis. So from the focus, if we go back at 45 degrees, where that line hits the line of eccentricity, I'm going to drop it, in this case, across, okay, and that is going to give us our vertex, which I'll put in with V. And the vertex is technically the apex of the parabola. Now, from here then, it's just a normal construction method to actually go off and draw our parabola, okay? So, what we have here, anyway, going through the focal line here, I'm going to put this line in blue. So I have a blue, I'll actually put it in yellow. That line there is known as, what's a funny kind of name, it's called the latus rectum. Okay, so I'll just write that in there, LR. Okay, now that we have that done, what we can take now is a series of ordinates to help us draw points on our parabolic curve. Now, usually between the focus and the vertex, there's kind of space there for one ordinate, so I'm going to roughly pick around the middle. These can be taken at random. So I'm going to do an ordinate like this, up and down, and the ordinate only needs to go as far as the line of eccentricity. Okay, so I'll do another one here. I'll do another one here. And I'll do one more here. Okay, the last one here, I actually will put this one in. I'll just extend it out there. Okay, now where each one of those ordinates hits the line of eccentricity, technically here, 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 and so on. The one that is the latus rectum technically is a point on our parabolic curve, so that's actually a point, but the other one hits here then as well. Now that one is not an ordinate because that one helps us get the vertex. Now, where every one of those hits the line of eccentricity, I'm going to use the widest one first, this one here. At that point there where it hits the line of eccentricity, I'm going to project it up to hit the latus rectum. Where it hits the latus rectum, I'm going to position my compass on the focus, set the distance on the compass to there, and rotate inwards like that. And that will always then help me find a point on my parabolic curve. So you can see we've got a point there, therefore the point at the other side is obviously here, because it's just showing us where that one was. I was just making sure, okay, so I'm happy with that. Now, how would I find the others? Well, from this one here, I'll also go up, this one here, up, this one here, up. Where the latus rectum and the line of eccentricity intersect, that is always going to be a point on our curve. Where this ordinate went across in this side, just because it's beyond the other side, I'm just going to go down. Okay, now let's get all those points. Now I'm going to set the distance for this point here where it went up. I'm going to rotate it back. That will help me find a point right there. But how do I find the point at the other side? Just mark it. Same thing with this one, set the distance to here, mark it down, mark it out the other side, same thing with this one, mark it out the other side. For this one here, I'll take the distance from here to the point and simply mark it out the other side. And finally, from this one, I'll just rotate back. And there we go. What I've found there now is a series of points on my parabolic curve. And just going to put little dots on them. Then job here after that then is to sketch it in. Now with your sketch, nice and easy, through there, up to here, into the vertex, and it should look symmetrical, and the curve should flow smoothly between the points. So now that I've got my points, sketch that curve in as best I can. So now that I've got the points, I'll sketch the curve in as best I can. And there we go. So there is our archway created with our parabolic curve. That's part A of the question done. Now the next part of the question, it tells us, draw a tangent to the curve from point P. Okay, now in regards to doing a tangent, sometimes they'll give you the point on the curve. In this case, they told us that point P is on the directrix. Now if there was a point on the curve, the method is you would go from the point on the curve to the focus, you would create a line. So let's say, just for argument's sake, that we had a point right here. You would connect it to the focus, and then that line there, you would go perpendicular to where it hits the directrix. Where it hits the directrix, that's another point in your tangent, you can draw your tangent. So in this case, it's just the same thing, only we're working from the directrix first. So if I connect P to the focus, I put that line in there, all I have to do here now is go perpendicular to that line, go perpendicular to that line from the focus. You'll see here where that goes through it, right here at this point right there, that is going to be a point on my tangent. And now all we do is we draw the tangent. They told us it starts at point P. Here we go. I'll draw the tangent in, and just for demonstration purposes, I'm going to put it in there with the pink. Okay, but what I will do is just highlight that. Just showing you there the method. And there we have the 90 degrees created. So all we did was P to the focus, we went perpendicular to where it intersects our parabolic curve to find, I suppose that there would be our point of contact, POC. Okay, and then we drew in our tangent. There you have it, guys. That there is part B of the question done. Okay. Now what we're going to do is we're going to move on to the second question on the exam paper, which was question A2. So over to this one here. Just the camera there, apologies. Okay, second question on the exam paper. 3D graphic below shows a trophy based on a pentagonal prism and a truncated square based prism. So you can see here we've got pentagonal prism here at the bottom and a truncated square based prism, but that has obviously been cut, leaving behind surface A here. Okay, on the right, a set of isometric axes is also shown, and the elevation and plan of the trophy, including the surface A, has been positioned relative to the axis. So we've been given the isometric axis. This is our y axis and our z axis, so yz, there's our y and z, because this view here is clearly showing it's actually an end elevation if that's the z axis. And then this view down here will be our x and our z, and that will be the plan view down here. So on the right, a set of isometric axes is also shown, the elevation and plan. Now they're saying elevation, in that case then I imagine that that should probably be the x and that. Okay, small thing there. On the right, a set of isometric axes is shown anyway, and then we've got surface A. Part A, complete the axonometric projection of the trophy. Okay, so what's nice about here is when this is isometric, basically what it means is that the axes are going at 30 degrees. So hopefully I have it set up correctly. Yeah, and you can see there it's at 30 degrees. So using my t-square set square, you can see there set up at 30 degrees. So I'll just zoom back in there. Now all that means is that all the points that I have down here, I want to build maybe the green object first, so the base. So all the points in the plan, you can see they've all kind of given you a guide here. They come up. So these are our projection lines. So we go up, up. There'll be a point here at the back. Probably don't see it, but I'll bring it up anyway. So very light lines, as you can see there. I'm after bringing them up. They're going projection lines. Now what I'm going to do is I'm going to find the points at the front. So if you wanted to use indexing, you could. Let's say we call this, just for demonstration purposes, A, B, C, D, and E. If I was to label those, well, C is the point at the front, so that's C. B is the point on the outside, there's A, because A is at the back, okay, when I'm looking in this direction. So it goes A, B, C, out to D, and then back into E. So, some people might struggle with that, so sometimes indexing helps. So, all we're going to do now is we want to find point C, bring it in at 30 degrees. Okay, let's find E. E is there, and D is already out there on the outside. So if I was to label those, or find those now, let's find C. That's where C is. That's where D is, and then we'll be back there. Okay, so I've kind of got the base part. Now what I want to do is I want to find the top part. Is that one there? Not sure if I see that one. We'll bring it in anyway. That one. That's already there, and that's already there. Okay, let's find the ones at the top. Very similar. Okay, now what I'm going to do is I'm going to draw that in. Well, that's kind of the prism there. I'm not saying I see all of it, but I drew it in anyway. So it always does help me with the visualization. Now, for the moment, I will maybe heavy in this just as far as about there. And this bit here just about there. Now for the moment I'm not going to heavy it in completely. The reason being is because I have another object here, which is the truncated prism here that I know I have to put in as well. Okay, so in regards to the truncated prism, I want to find where those points are. Now what's helpful here is I want to find, you can see the points have already been projected technically. I'm going to extend them down a bit further. They'll come down here. That one's already down there, and this one just needs to come a bit further. Now I want to find those points. Once again, I could use a little bit of indexing. I'll go to red this time. And let's say I call this point here at the back. Let's say I call this one here at the front number 1. Let's say number 2. 3 is at the back, and 4. Now I'm just focusing on the prism. Well, number 1 would be at the front in the middle. Number 2 would be on the left. I'd have number 3 in the middle as well. And then 4 will be here. So if I was to find those now, okay, well, where would number 1 be? Number 1 would have to be where I projected up, and it looks like number 2 is in the same position, to be honest. So 1 and 2 will come up, and 4 and 3 will come up. So if I was to find those, well, that looks like number 1, number 2, number 3, and looking at it there, I think that's number 4. Once again, I like to visualize it, so I often draw it in. So I've kind of got the base of the prism. Now it looks to be going vertically up, so that's going to go up. That's going to go up. And now it's about finding those cut surfaces. Now, we want to find where number 1, the edge for number 1, you can see it here, where that ends. So how do I find where that point ends? I want to find surface A now. If I bring this down, okay, that's going to show me where surface A is there. So I'm going to heavy this in now. Okay, I'm also going to heavy in this. Now, I've essentially found this point. The next point I want to find is the point where number 2 ends, which is the height there. How do I find where number 2 is? Bring it down, and I found it right there. So, number 1 connects up to number 2, so that's actually just going to be a vertical line. That's actually really handy for us. Excuse me. Excuse me. So I found number 1, which is right here. I'll actually write the numbers in. Here's where number 1 was. Number 2 was up there. Now I have a point in between it, between the 2 and the 3, which is right there. How do I find that? So that point up there, that's going to come up to here. Now it comes up there like this, and where's the point? Well, that's clearly the point up here in the elevation, as they call it, and that's going to show to me where that point is. So you can see I followed it up. So what do? Let's join it up. There we go. Now the other point I want to find is this one. That's on the cut surface there. Okay, so that will go up, which it already has. This guy has to come down. That's going to show it to me right there. Okay, so now I've found that one. The next point I want to find is this one. That line has already been brought up, but I have to bring it down here. And that's going to show me that one there. So that's actually going to connect down to here. I'll go the whole way, but the point that I found would have to connect down to here. This is going back to the points that I had at the start. And there we go. Now I can actually, heavy in this bit, I can see how far that goes back. There's no need to show hidden detail in an axonometric view. Now we're just forgetting the little surface here at the top. Now that guy there would come from the center at the top. Now people might have kind of forgotten about that. So how would I actually find that? Now that guy will go up. You could find a point up here in the middle and bring it down, and you'd end up getting it there. And I think that's actually the way I'm going to do it. Or you could do sliding set squares with the edge here from this point. I think the easiest way to do it though is find the middle here. So how would I find the middle of that point there? Because if it's in the middle here, okay, you can see between 2 and 4, point number 3 would have to be in the middle there. So if I just extended this guy up, it's a bit hard to see it there now with the colour on the screen. But from that point right there, I'll extend it down. Different ways of going about it. You could bisect it as well. And there we go. And that'll simply connect over to here. So a nice little question there now. Quite detailed. Okay, there you have it guys. That there is completely axonometric. Okay, and just for demonstration purposes, it was in blue. So I will put it back in blue as well. Where's the cut surface A? Poorly coloured in there, but you can hopefully see that. Okay, there is my cut surface A. Now part B of the question, it says here, show the true inclination of the surface A to the horizontal plane. Now basically what they're saying is, what angle does surface A, even though it's this kind of like irregular pentagon, okay, because all the sides are not the same length, it's an irregular pentagon. Essentially what they're saying is, what angle does that surface make with the horizontal plane, the ground, or any flat surface that would be parallel with the ground? Now, essentially what we're kind of getting at here is we want to see that surface as an edge view. So if you think of it, even though we're in axonometric, this is an elevation, this is a plan. In any view of these, have I got a line that is showing a true length? Okay. Now, if I want to see a plan view, okay, or I want to see the ground as a horizontal line, I'll actually have to take an auxiliary view from the plan. Okay, if I take an auxiliary view from the plan, we're going to take our heights from the elevation. Think of this line as the baseline, that's the ground line, okay, and I can take my heights from the XY line, or that line, the ground up. Okay, now essentially what I want to find is, I want to find surface A as an edge. So I'm going to take an auxiliary view. Okay, and how do I take an auxiliary view? Well, I need to find a true length on surface A. Now if we look at the lines on surface A, are any of them a true length in the plan? Well, that line there is not a true length. Why is it not a true length this little bit? Well, because the line in elevation is not horizontal. And I can see it's not horizontal, not horizontal, not horizontal. But the line here at the very, very tip top is parallel with the ground. Therefore, it is a horizontal line. Therefore, that is a true length. So if I set up my x1, y1, okay, perpendicular to that, I will then see it as a point view. So what I'm going to do is I'm going to project out, quite hard here now, it's quite detailed. I'm going to project out this way, and do it out here. Okay, I'm going to project out these 2 points, 2 and 4. You can see that they're in line. Project out point number 1. So they're all gone out there. And if I rotate my set square, I'm going to set it up just out here. Now it might go out a little bit, but we'll see. It might go into the, we'll do it in here actually. This there is my x1, y1. Because I projected from the plan, I will take my heights from the elevation. Now, the heights I want to take are for the points. So the lowest point here, point number 1, is this height up. So if I take that height from there, you could technically actually, to make my life a bit easier, no, I'll just take it from here, it's fine. You could take your heights from this line, but I'm just going to take them from the ground. That's the height for that. Mark it up, that's the point, follow it out. I'm going to take the height for the next one. That height there is the same as the height over here, which is this point, point 2 and 4. Follow it out. And finally the last one will be the height up to the very, very tip top. I'll mark it out from the third one. It's kind of gone into my drawing there. It was my own poor choice of maybe where I'd chosen to do from. Okay, I'll extend that out. Now essentially, those points that I found are point views of those points on the surface. This one here is 2 points. These 2 points are seen as a point here. And what happens is I should see all the points connect as a line. That is the surface when I see it as a line. But more importantly, if I extend it down, I can find the angle it makes with the ground, which in this case is the x1, y1. And that is the angle of inclination inside there. Now on the day of an exam, I probably should measure it. I will. And I'm reading that as, there we go. I'll just extend the line a little bit further so I can take an accurate measurement. Okay, should extend it down here as well. I'm reading that to be about 56 degrees, it looks like to me. Right there. 56 degrees angle of inclination. Surface A. Okay, and there we go. There you have it, folks. That there is the second question on the page, A2, which is based on the topic of axonometric. Nice little tricky part there for the part B of the question though, where we had to find the angle that surface A makes with the horizontal plane. So, question 3. This question here kind of has a lot to do with solids in contact and your understanding of this. So it says here, the image on the right shows a round bale trailer. The trailer can load and unload bales by rotating them on and off the platform of the trailer. So we can see here, they're actually showing the rear of the trailer. It's like we're looking in at the back of it, and we can see the bale as it sits on top of the trailer. The drawing below shows an end view, okay, of a similar trailer showing bale A and bale B. Okay, so we've got bale A, which is actually obviously on the ground, it's not on the trailer. It tells us then, part A, rotate bale A anti-clockwise. So anti-clockwise, so if you think of anti-clockwise, we're going in this direction. Okay, we're going in that direction, anti-clockwise, about point P, so they give us point P here, until it touches the axis x1, y1, and you can see that axis x1, y1. Now, what they do tell us is, they give us the rotation point, which is point P, and they also give us the size of the bale, which is really helpful, so we have the radius as well. Now, what I know is, if that bale has to sit on the trailer, essentially it just has to rotate up here. It has to touch both the trailer, but they also want us to stop at the axis line. So, what I'm actually going to do here is, I'm actually going to take the radius here of the bale. I'll take the radius of the bale, and I'll mark it out from the axis. So you can see there, I took the radius, I went to that axis line and I marked it out. Therefore, I know that the center point, okay, the center point of the bale has to be somewhere up along that line. Okay, so now what I'm going to do is I'm going to rotate the bale using point P into the center. I'm going to rotate the center of the bale, okay, until it goes up to there. Alright, now that I've rotated it up to there, what should end up happening here is that should be my center point, okay, when it's in its correct position. That should be the center point. So now that I've got that center point, what I'm going to do is I'll draw a line across there, take the radius of this guy, draw it here. No, not the neatest possibly. There we go. I can see that I've drawn the bale for part A in its correct position, and they haven't asked us for any points of contact or anything like that, but I will put them in. But just for demonstration purposes, I'm going to heavy that in now a little bit better, just with my fine liner. So let's go over that now. Make it stand out a little bit more on the drawing. And there we go. Now, technically, where would our point of contact be? Our point of contact will be right here, because that's the point where it's also touching it. Okay, it's technically touching the other bale at a point there, but I'm going to read the next part of the question. So that's part A done. All we've done is we've rotated about point P until it's sitting up there on top of the trailer and hit the axis XX1, or sorry, X1, Y1. Now, part B, rotate bale B, which is the second bale, anti-clockwise again. So we're actually going back in the same direction, like the first one. We're going anti-clockwise about point P1 until it touches the XY line. So basically what they're saying is bring it down here. They're basically just giving us a set of instructions to rotate it until it touches the XY line. Now, what I'm going to do here is I'm going to rotate that. So I'll actually start the rotation first this time. It looks to me like the bales are similar size. Can't guarantee it though. So what I'm going to do is I'm going to take the center point. I'm going to rotate it down. So the center point would simply rotate down. Now, how do I find the height of the center? Well, what I'm going to do is I'm going to take this radius of the bale. I'll take the radius of the bale. I'll actually do a line up over here. Just do it out here. And I'll mark that radius up along that line. So just check it here. Yep. Mark the radius up along the vertical line because it has to touch the ground, and then I know that's the height of the center above the ground. So if I bring it across at that point there, that is the exact position of my center. And now I could draw a line down, same thing again, that's my center, draw it in, and that's the position of the bale when it's on the ground. Same principle here. What we're going to do is just heavy it in using our fine liner. Just take my time with that now. And there we go. And what we have there now, that's the point of contact when it touches the ground. Very, very handy question there for a higher level question. All they're basically saying is they wanted us to rotate one bale up onto the trailer and one bale off the trailer. Essentially the same principle both ways, okay? So you have it, guys. That there was question A3 done. Now what we're going to do is going to move on to A4 at the bottom right. Okay, so in this question here, A4, the image below shows a tablet. We can see the little tablet here with a cover case stand. So we got the little stand at the back of it. It tells us then the drawing on the right shows the plan and partial elevation of a similar tablet. Complete the elevation of the slope surface or the slope screen ABCD. Okay, so they basically want us to kind of complete the elevation up here. And this kind of has a bit of a principle to do with the oblique plane. Now, if you look at the edges A and B are clearly on the ground. Okay, so what's helpful here? I'm just going to focus on the outline first before I actually do the bevel there on the screen. So if I bring up A, that's going to be the position of A when it is in elevation. So that's the new position for A. Now what I want to do is I want to find the position for D. Now what's really helpful here is there's a principle here we learn in graphics, or sorry, in DCG, and that principle is that lines that are parallel in orthographic views will remain parallel in all orthographic views. So I can see that the line AB is parallel with the line DC. Therefore, the line DC in elevation has to be parallel. So if AB is a horizontal line, well then so is CD, or DC, however you want to call it. So therefore, I have now found the position of D. And now that I've found the position of D, I know D can connect back down to A. And what you'll notice is the line AD is parallel to BC, because they're both parallel in the plane as well. So there we have starting point. And what's great about that little principle is that'll actually help us figure out the bevel on the inside as well. Just heavy that in. Okay, so that there is the outline. Bit of a bleed there, apologies. Now, what I want to do is I want to find these guys here. So if I want to find the bottom edge, I'll bring it up. It's going to be somewhere up there. Now, I have an oblique plane here, so what I could do, you could get straight, so we're not going to do that. But if I extended this edge here, so if I wanted to find the bottom edge, if I extend that edge out to here, just like that, if I was to extend that out, what I've essentially found here is a point right there on the outside edge. But I know then that that line there is parallel, so if I can find that point on the outside edge, should be sharpening my pencil here, bring that up, and see it right there, comes up to here. Now you can get little discrepancies depending on the thickness of your pencil, but you can see, I'll try and draw that in a little bit better. There we go. And now it's hitting up about here. What am I going to do from there? I'm going to go across. And you can see then, where it goes across, I have now found a point and a point. So now I can heavy in my bottom edge. So now that I've got the bottom edge done, I want to work on the top edge. Excuse me. So now that I have the bottom edge done, I want to work on the top edge. So to get the top edge, okay, all I'm going to do is I'm going to bring up the points at the bottom in the plan. They're going to go up and up. Now, rule of thumb here, okay, I could bring a line across, go up and across, but I know the lines are parallel in plan, therefore they have to be parallel in elevation. So, if they're parallel in plan, they'll be parallel in elevation. So, if I use sliding set squares, and there we go. If I do sliding set squares here, now it should be parallel. What should happen here? Let's see what Marcus is like. Not bad. And there we go. That's a nice little question. Just heavy that in now. And there we go, part A complete. Complete the elevation of the slope screen ABCD. Now, part B, determine the true shape of the surface ABCD. Now, what they're basically saying is we want to know what that surface is, just ABCD, not the bevel inside it, okay, for the screen, but just the actual surface ABCD, the outline. And we want to see the true shape of that. Now, there's a couple of ways you could go about this, okay. One way is that you could take an auxiliary to see ABCD as an edge view and then rotate it back and rabat it down and get the true shape here. Or you could actually just work out the actual lengths of it. Now what's really helpful here is, do we have any true lengths? Because essentially it's just a rectangle we have to draw. Are any surfaces in the plan a true length, or even in elevation? Well, like if we look at the plan here, the surface AB, or the line AB I should say, and the line DC, they are actually both true lengths. Why are they true lengths? Well, the principle is if the lines are parallel to one of the principal planes, in the other view they will be a true length. And if you look at the line DC here, or the line AB, you can see that those two lines are sitting parallel to the XY line. In this case, AB is even on the XY line. Therefore, AB is actually a horizontal trace. But those lines there are parallel, therefore in plan they're true lengths. So that's really helpful. So if I know that they're true lengths, the only lines I actually need to get the true lengths of then are the lines AD and BC, which are the same length. So once I have one of them, I can find the other. So the easiest way to use to get that is actually to use the principle of a cone. Okay, so if I was to, let's say I'm just thinking here, would I have enough room? I think I do. I'm going to use C as the apex of a cone. Imagine that this was a cone, okay, and CB is the generator of said cone. So if I was to extend out C like this, and I know B is on the ground because that's on the base point or the base circumference of the cone. If I was to rotate that until it's horizontal, so I'm going to treat C as the apex of a cone. I'm going to rotate B. There we go. I'm going to rotate B until it's in a new position, which I'm just going to call here now B1. Well, I've rotated B in plan, so if B rotates in plan, it should also rotate in elevation. Now, because that's rotated in elevation, B is not here anymore. It's essentially that arc that happens in the plan view. That's essentially a horizontal line in elevation. That's B1. Okay, but more importantly, what have I found? I have found the true length between C and B. That length there is the true length C to B. Okay, so I'm after working out what is the true length. Now that I have the true length, essentially if I was to take this surface and flip it over, A and B is on the ground, and flip it over like a hinge, okay, I could find it out here. So if I was just to simply extend those faces out, this is the easy way. This is kind of a rebatment. If I was to extend those out, and all I have to do now is take the true length from there to there and add it on. Just squeezing onto my page there. And there we go. Now, draw that in. Technically, there to there to there. What I have now found, well, that was AB. I've got D has kind of flipped over. Let's call this D1 and C1, but more importantly, true shape A, B, C, D. Now there is one other way we could have done this. I'm hoping my accuracy will work out in this. We could technically have taken an auxiliary view where we see the surface A, B, C, D as an edge view, and I will do it here just really quickly to prove a point, hopefully. So if I was to project out A and B, projecting from the plan, taking our heights from the elevation, and CD, I'm going to set up an X1, Y1 perpendicular to my projection. That's my X1, Y1. Normal rule of thumb here applies. If I project it from the plan, I'll take my heights from the elevation. A and B are both on the ground, so they will actually be seen in this position here as a point view. So that will be A1, comma B1 as a point view. But how do I get the heights for C and D? Well, simply just take them. Take the heights here. Follow C and D out. Markers from the X1, Y1. Just about gone into my drawing there. Join it back to here. What I've essentially found there in that position is C1, comma D1. Okay. Now, essentially what I have here is the angle of inclination that surface makes with the horizontal plane. But I don't really want that. What they've asked me for is the true shape. Okay. So if I wanted to get the true shape using this method, I could use the principle of a rebattement. Imagine the ground was extended. I could take this surface and rotate it until it goes onto the ground. Now A and B, as I said, is the hinge. It's kind of like what we did here. Now we're just kind of, I suppose, proving our principle here. Take this guy, rotate it around. It's like I've taken that surface and I'm rotating it, okay, until C and D, C1, comma D1 are in a new position, and then once it's been rotated, just imagine you have to bring it back, and it's actually probably out by about 0.5 mil, not bad. Imagine I had to bring it back and then extend it out, and that's another way of kind of showing that that surface has been rotated onto the ground. That's kind of what's after happening here, okay. So there you have it, folks. They were the 4 questions, the 4 short questions from the DCG mock there 2026 from the ExamCraft company. Kind of nice questions, okay. That one there, probably very simple one. I wouldn't usually expect something that easy. Most students should have been able to get on okay with that. This bit here probably caught out quite a lot of students, okay. That bit might have caught out students, okay, and then obviously a parabola one if you've done that. There are the questions complete, guys. I hope you found those helpful. Okay.